Okay, here's a thing that, by all rights, shouldn't work. Two spacecraft, each one moving at 17,500 miles an hour. And somehow they've got to find each other up there and lock together without crashing. So what's the hard part? You're probably already picking one. The speed, that ridiculous number, or the distance, finding each other in all that empty space, or maybe the docking itself, actually lining two vehicles up and connecting them. It's none of those. The hard part is something stranger, because up in orbit, the most natural move you can picture, spot the thing you want, point your ship at it, fire the engine to catch up, does the opposite of what you'd expect. You go straight at another spacecraft, and you don't catch it. You fall behind. Every vehicle that's ever pulled up to a space station had to get past this. So will everyone we send back to the moon. And getting past it means doing the most backward-sounding thing in all of spaceflight. To catch something that's ahead of you, you first slow down. So that's where we're headed, why that works, and how two objects moving around the planet at 17,500 miles an hour end up meeting at the speed of a slow walk. I want to stay on that number for a second, because it really does feel like the whole problem. But it's almost beside the point. Let me show you why. Picture one of the most famous maneuvers in spaceflight. On the way to the moon, the Apollo command module had to turn around and dock with the lunar lander riding behind it, and the whole time, both of them are coasting away from Earth at something like 24,000 miles an hour. So how hard was that final connection? They came together at a fraction of a foot per second, a slow drift, nothing more. And the reason is that both craft were moving at that same enormous speed. So between the two of them, the speed simply wasn't there. That's the trick. The speed was never the thing that could hurt you. It's the difference between them. And that means slow down isn't really the goal either. Both vehicles hold their orbital speed the whole way. They have to, or they drop out of orbit. What you're actually doing is shrinking the difference between them down to almost nothing. And not just the gap in distance. The difference in which way they're pointed, how fast they're going, even the slow turn of each one. Match all of it, and two objects hurtling around the planet become, relative to each other, nearly still. So that's the goal. The trouble is, the moment you go to actually do it, your intuition turns out to be wrong, and not by a little. To see why, you need to know what an orbit really is, because it's probably not the picture in your head. An orbit is falling. That's the whole secret. A spacecraft in orbit is being pulled straight down toward Earth by gravity every second, exactly like a coin dropped off a rooftop. The only difference is that it's also moving sideways so fast that the ground curves away beneath it just as fast as it falls. So it falls and it misses, falls and misses, over and over. Now here's the one fact this whole thing depends on. How fast you go around the Earth comes down to how high up you are. Down low, you're fast. Up high, you're slow. Drop in closer to the planet and you come around quicker. Climb higher and every lap takes longer. Partly because you're moving slower, partly because it's a bigger loop to cover. Hold on to that, because here comes the trap. The exact one that caught the first crew who ever tried this. You're the chasing ship, trailing your target, same orbit, and you want to close the gap. So you do the obvious thing. Point at it, fire the engine, speed up. But speeding up doesn't carry you forward toward it. It lifts you into a higher orbit. And a higher orbit, as we just said, is a slower one, with farther to travel. So one lap later, you're not closer. You've slipped behind the very thing you were chasing. And this isn't a chalkboard thought experiment. The very first time anyone tried it for real, an astronaut set out to pull up alongside a spent rocket stage. He did the obvious thing, pointed straight at it, and burned toward it. and the harder he chased, the more it slid away. He burned through fuel he couldn't spare and never reached it. So if going straight at the target only drops you behind, the fix is the thing that sounds wrong out loud. To catch something ahead of you, you slow down. Here's what that actually does. Slow down and you sink into a lower orbit, a faster one, with less ground to cover. Now you're gaining on your target every lap, creeping up on it from below and behind. And once you've pulled far enough ahead, you speed back up, rise into its orbit, and settle onto the same path it's traveling. Up here, to go faster, you drop lower. To catch up, you fall back first. None of this was obvious. It took real work to figure out. One of the astronauts who'd later walk on the moon, Buzz Aldrin, earned a doctorate in this exact problem before he ever flew. His thesis was on orbital rendezvous, and the other astronauts started calling him Dr. Rendezvous. The motion between two spacecraft this close together is so slippery that it has its own set of equations, first written down back in 1960. The first proof it actually worked came soon after. December 1965, two crewed capsules found each other in orbit for the very first time and flew in formation about a foot apart. Close enough for the crews to look across and see each other through the windows. They couldn't dock. Those capsules weren't built for it, but they'd shown the hard part was possible. Two spacecraft could meet out there in the dark and hold steady, nose to nose. And Aldrin got to test his own theory about a year later. Partway through his rendezvous, the radar lost its lock. The instrument meant to guide him to the target simply quit. So the man who'd written the thesis became the backup computer himself, taking angles to the target with a handheld sextant, running the numbers on a slide rule, and talking his commander through the final approach. They docked anyway, reportedly on less fuel than crews who'd had a working computer the whole time. And it's the same move that later brought crews home from the moon. A lander lifting off the surface didn't rise straight up to the command module waiting in orbit above. It slipped into a lower, faster orbit and closed on it over the next orbit or two. The exact same logic, 250,000 miles from home. But matching orbits only gets you so close, within a few hundred meters or so. In space terms, that's practically touching. And those last few hundred meters turn out to have a problem all their own. The same effects that made chasing fail don't ease off up close. They take over. Even here, you cannot simply point and push. Fire a thruster straight at a target 100 meters away, and your path bends away from it. At close range, traveling in a straight line is the hard thing. So spacecraft don't charge in. They follow carefully chosen approach lines, usually rising straight toward the target from directly below, or sliding in along its direction of travel, from in front or behind. These paths aren't picked for speed. They're picked because they're safe. If the engines quit at the worst possible moment, the natural drift carries the chaser away from the target, not into it. On the newest vehicles, no one needs to fly this by hand. A capsule like SpaceX's Dragon runs the entire approach itself, narrowing from hundreds of meters to a few while bleeding off speed the whole way. And then comes the part that has to be gentlest of all, the moment of contact. The first time two spacecraft ever docked, in March 1966, the crew nearly didn't make it home. The docking itself worked, but half an hour later, a stuck thruster sent the joined vehicles tumbling, faster and faster, until the crew were close to blacking out, and only an emergency move with the re-entry thrusters saved them. It was a vivid reminder of the stakes. Out here, with two massive objects moving this fast, there's no room for anything sudden. The connection between two spacecraft is engineered to be slow, gentle, and above all forgiving. So it happens in two stages. First, soft capture. As the vehicles meet, a mechanism reaches out and catches loosely, with give built in, soaking up the last of the motion, the small wobbles, the slight misalignments, so nothing jolts. Only then comes hard capture. Hooks draw the two craft tight, metal seats against metal, and a ring of seals presses home to make the joint airtight, so a crew can eventually open a hatch and float through without a suit. And here's the strange part, that final contact is easier in space than the closest thing we attempt on Earth. The oldest docking method is a probe and a cone. A spike on one vehicle slides into a funnel on the other and locks. It's the same probe and drogue idea military jets have used to refuel in midair since 1949. But aerial refueling is, in some ways, the harder job. Two aircraft hooking up are fighting moving air the whole time. Turbulence, gusts, the shove of the slipstream. Each pilot holding formation against forces that never let up. Two spacecraft have no air to fight. Once they've matched velocities, nothing pushes them apart. They simply hang together, and the connection becomes the calmest part of the entire journey. That calm is what makes everything after it possible. The hardware has been refined so that either vehicle can take the active role. An idea that traces back to the first link-up between an American and a Soviet spacecraft in 1975, and refined further until no crew is needed at all. Some arriving vehicles don't even fly themselves in. They hold still nearby and let a robotic arm reach out, grab them, and berth them onto a port by hand. It's how an entire outpost can be assembled from pieces that arrive separately and join on. So after all of it, how fast are the two vehicles actually moving when they finally touch? Almost nothing. At the instant of contact, both vehicles still circling the planet at roughly 17,500 miles an hour. They come together at something close to 1/10 of a meter per second. That's the whole answer in a single image. The real work was everything else. Reading the backward rules of falling, slowing down in order to catch up, curving in along a path built to stay safe even if everything fails, and squeezing the difference between two spacecraft down from miles per second to the pace of a slow walk. They don't slam together at 17,500 miles an hour. They agree, step by step, to move as one. And then, barely moving at all, they touch.